Hello everyone and welcome to the fifth module in the six-part training series on the FR5969 launchpad. In this module, we will learn about the MSP430's 12-bit differential ADC known as the ADC12B. This module will also cover two labs based on the ADC12B peripheral. The FR59 device features the lowest power ADC in the MSP430 family that is capable of operation down to 1.8 volts. This 12-bit differential ADC uses the common reference or ref module to select an internal voltage source or can use AVCC as a reference. Each input channel comes equipped with its own configuration register, allowing full configurability of clock source, reference, and memory control on a per-channel basis. The ADC also provides internal connections for temperature and battery measurement. DMA capability allows the storage of conversion results into memory without CPU intervention. A new feature on this ADC is the window comparator. The following slides will cover this feature in more detail. The ADC window comparator allows the user to set threshold levels for conversion results. Two levels, a low and a high, can be set. The ADC compares the converted result with these threshold levels and can provide an interrupt if the result is below, above, or in between the thresholds. When this feature is used in combination with the DMA, the CPU can be turned off for a majority of the time. This is especially true if it only needs to act on conversions that fall within a specified range. Now, let's look at an example when the window comparator flags are fired. Consider the input signal shown on this slide. You can see how the ADC window comparator flags are set in conjunction with the signal passing the threshold levels. The next feature we will talk about is differential mode. Differential input signals are useful since they offer better noise cancellation. Using a differential input also doubles the ADC's dynamic range. One of the key features of the ADC12B is the ability to combine two ADC input channels to create a differential input channel. This is done by setting the ADC12 diff bit in the ADC12 control register. In this mode, the difference between the two input channels is measured and stored in the ADC12 memory register. When compared to single-ended usage, the ADC conversion formula and the impact of data format differs significantly in differential mode. Refer to the user's guide for notes on how to evaluate the ADC's conversion results in this mode. The ADC12 also provides a method to map internal channels such as battery and temperature measurement. The battery measurement steps down the supply rail to half AVCC. Now let's learn how to use the ADC in the first lab. The source code for this lab, as well as this PowerPoint presentation, is available from the link shown on the slide. An easy way to find it is to go to processors.wiki.tia.com and then search for the term FR59XX Training Workshop. On the wiki page, browse to the launchpad section and download the lab zip file from the link marked Lab Material. On opening the zip file, copy and paste both folders Lab 2A and Lab 2B into your workspace directory. Now both projects for the following labs are set up. The goal of this lab is to sample an analog input channel A2. The start of conversion is controlled in software. The conversion result is analyzed to see if the input voltage is above or below half AVCC. An LED is turned on or off based on the result. In the next lab, we will modify the settings used here but make the code more efficient for ultra-low power operation. This slide lists the different settings you will need to configure in this lab. This flowchart shows the program flow we described in the previous slide. The slide also highlights the functions handled by the ADC module in hardware and the processing performed by the CPU in software. In this lab example, since much of the post-data processing is done in software, the device has a high active duty cycle. To begin the lab, open the source code lab 2A adc12b.c in the project folder. You can use the comments as a guide and set up the ADC using driver library as explained in training module 4. Once the lab exercise is complete, you can test your code by tying the ADC input channel to VCC or ground to check whether the LED turns on or stays off. Now let's talk about how to configure the ADC. The first step is to initialize the ADC using driver library. We would like to set up the ADC to use a software trigger. We also want to use mod_OSC as the clock source for the sampling clock and not use any clock dividers. Use the driverlib API documentation to learn about the arguments that need to be passed to this init function. Once you have filled out your answers, check it against the solution. Next, we enable the ADC and set up the sampling timer. The cycle hold argument shown on this slide specifies the number of sample clocks that are needed per sample of the ADC. The first cycle hold parameter defines the sample time for channels 0 to 7, and the second parameter defines sample time for channels 8 to 15. In this case, we only care about the first argument since we are using channel A2. Set up this parameter for 16 ADC clocks. Check your answers against the solution to see if they match. Now we configure the memory control register. We can set up this register such that the conversion result from A2 is mapped to memory control 0. Also remember to set up the reference as AVCC. Other options for setup are provided in the comments. Next, we set up the interrupts. Enable the interrupt IE0 for the ADC12 since this maps to memory control 0, which is the memory control register being written to. This slide shows the API calls for the interrupt flag clear and enable. Now we set up the function that triggers the start of conversion. We also need to make sure the ADC is configured to single channel, single conversion mode. Using the single conversion mode means that software will be required to set the start of conversion bit each time a sample is required. Check your settings against the solution. The next step is to set up the decision logic in software. Remember, half AVCC needs to be expressed as a hex conversion result. You will also need to set up the GPIO port P1.0 to turn the LED on or off based on the conversion result. Once this stage is complete, we can move to the interrupt service routine. The interrupt service is already pre-populated in the source code. Enabling the IE ensures that the interrupt flag is set and the code execution vectors to the interrupt service routine. You can set up a function to read the converted result from the ADC inside the ISR as shown. Build the code to ensure that all the blanks are filled and there are no errors. Download the code to the launchpad and allow it to execute. Once the code starts executing, terminate the debug session. Now you can measure the current consumption of the system. This is done by removing jumper J9 and placing a multimeter in series. The multimeter should measure around 230 microamps. The reason for this number is because the code example does not use all of the means available to tune the code for low power. The next lab uses the window comparator feature that drastically reduces the power measured here. In the second lab, we change some of the settings we previously used. The main goal here is to make the sample conversion cycle fully automatic. Also, the decision control is removed from software and done in hardware using the window comparator. This brings about even more power savings. Using the window comparator ensures that the CPU does not need to wake up to compare the conversion result and set the threshold value. The ADC only interrupts the CPU if the conversion result is within the specified thresholds. This helps the application maximize the time spent in standby mode. The flowchart outlines the sequence of events and the decision logic. The flow starts with the timer triggering the start of conversion, followed by which the ADC takes a sample on channel A2. The converted result is then compared against the window comparator thresholds. Depending on the result, the CPU is turned on to turn an LED on or off. The device then returns to LPM to wait for the next timer-triggered conversion. The second lab uses the lab folder 2B. Open the source code lab 2B ADC12 lowpower.c and fill in the blanks as before. There are a few changes in the configuration settings. The init function now uses successive conversions triggered by timer A0.1. The ADC is also set to sample at a slower speed to help conserve power. Once you set up the init function using driver library based on the comments, check your answers against the solution to see if they match. Next, when configuring the memory control, remember to enable the window comparator. Also use the window comparator API to set up the high and low thresholds. This slide shows how that can be done. Now we enable the interrupts for the window comparator instead of the generic ADC interrupt. This slide shows how this is done. We also need to use driver library to set up the timer to jump-start the ADC conversions. The ADC is set up to perform repeated conversions of a single channel. In the main loop, the decision logic toggles the LED based on the window comparator interrupt that was fired. Also, the high and low interrupt enables are toggled in this function. This slide shows the decision logic for if the ADC data is set to 1. This slide shows the logic for the else condition. Build the code to ensure that all the blanks are filled and that there are no errors. Download the code to the launchpad and allow it to execute. Once the code starts executing, terminate the debug session. Now we will measure the current consumption of the system. This is done by removing jumper J9 and placing a multimeter in series as we did in Lab 2A. The current measurement should be around 75 microamps. So what contributes to the power savings compared to the previous lab? There are three significant factors that contribute to lower power. 1. The automatic timer triggers of the ADC to start conversion ensure that software is no longer needed. 2. Using the ADC in consecutive sampling mode to prevent CPU intervention. And 3, and perhaps most important, the window comparator logic that only provides interrupts when the ADC conversion result falls within a user-specified threshold. Moving from Lab 2A to 2B, we have learned how to configure the ADC for low power operation. I hope that these labs were useful in learning the functions of the ADC 12B module.